All right, we've talked about temperature now as a variable in the atmosphere, and you all wrote some very interesting discussions and all about how it changes. Well, one of the things that temperature influences is pressure, and pressure can influence temperature as well. But why do I care about pressure as a meteorologist? So, we talked about surface weather maps. You've looked at them several times now. Well, here is just one for today. And there's nothing special about it except there's high pressure over the Great Lakes, 1035 millibars, and there's low pressure off of Boston, around 996 millibars, it looks like. So, two areas. We know that low pressure tends to bring bad weather and high pressure tends to bring good weather. But why? So, this is what we're going to discuss a little bit. What causes high pressure or what causes low pressure? And as part of that, we're going to talk and look a little bit at the vertical components of the atmosphere. Interestingly, we know temperatures drop with height. So let's take a look a little bit at that. For example, here's Atlanta's weather today. Notice, actually, this is not Atlanta. This is Great Falls, Montana. And you can see the temperature decreased with height pretty steadily here. And just a little bit above freezing today. But it's quite cold up to, we talked about the tropopause. Well, if I had to make an estimate, I would say the tropopause is right about there. A little bit above 300 millibars, between 250 and 300. Right where the temperature begins to increase. Now we look at Atlanta, for example, and we discover that, temperatures have fallen off right off the surface here. Well, we learned a little bit about cooling at night and how temperatures cool quickly. Well, they don't cool quite as quickly when you get further up in the atmosphere. So with that in mind, what happened here is temperatures dropped off at night, a little bit warmer above, so you get an inversion. You have another one here because there's actually a front that went through Atlanta. Fronts are sloped. So as it went through, it's only reached an altitude of a little bit over 800 millibars right now. So you can see there's a difference depending on temperatures, depending on where the front goes, what time of day it is. And temperatures decrease pretty steadily again once you get over here. So let's take a little bit more of a look at pressure. Why are we interested in it? So what's the significance of both pressure changes in the horizontal and vertical? So with that, let's learn what pressure is first. It is a force. Everything can exert a force on something else. Literally, our bodies are pushing back and push a force at the air. That's why our bodies don't collapse. Air pushes a force on our house, and the house pushes back. So that is what air weighs because of all the molecules and the way they move. Air has weight, which is a type of a force. Dalton's law, all it says is that, the air is made up of nitrogen, oxygen, water vapor, argon, carbon dioxide. I can go on. But each one of these has a pressure. Some are very small, some are much bigger. The total air pressure of the atmosphere is accumulation of each one of those gases and their pressures. So if I know the pressure of one, I know the pressure of another, and so on, I can add up the total air pressure. So, two things. The kinetic energy of the molecules, which are the motion temperature, really, and the mass. In other words, if I have an area carved out in the atmosphere, Could be 1 meter by 1 meter. It could be 1 inch by 1 inch. I don't care. In that area are so many molecules. Density is how many molecules are in that area. So in other words, more molecules are in that little area, the more dense it is. And if the density is higher, temperature was the same, you would have more air pressure. If the density was lower, even if you had the same temperature, the air pressure would go down. So density and temperature, they control air pressure. How do we measure a temperature? How do we measure pressure? Old days was a mercury barometer. They found it interesting. Somebody put a tube that had filled to the top with mercury. They had a little bowl below it that had mercury in it. They pushed that tube with their finger over it or whatever into the mercury. Now, some of the mercury in the tube came out, but the rest stayed up in the tube. How the heck did it stay up in that tube? Well, they stayed up because that was the air pressure. So that was measured in inches, the column. So that's how we get things like 29.85 inches or 30.25 inches of mercury, because they were measured back in the day. But this was the first estimates we ever had of air pressure, and learned that, oh, gee, air has weight. And these are different units of air pressure. Most of you are familiar with inches of mercury. However, as a meteorologist, I will tend to use millibars, which literally are the same as kilopascals or pascals. So those are the two main units of measure that we use. So, interestingly, air is compressible. I want you to think about something a minute. If you got a bottle of water, if you squeezed on that bottle, it's pretty tough to squeeze it together. And if you pop the top off, it would come pouring right out, because water is an incompressible fluid. In other words, you can't compress it. It doesn't want to be compressed. So it really takes a lot of effort to do that. Air, on the other hand, well, think about a pump. When you're pumping air into a tire, you're compressing what used to be air spaced out into a much smaller area. The reason you do that is you're putting more molecules into your tire, making the density greater or making the air pressure higher. So air is compressible. That is a big difference between water and other fluids. While air is compressible, it's pretty much one of the only ones that is. High pressure systems, low pressure systems move by you. Every day, the pressure is constantly changing. It probably will change lower with high pressure over you than it will with low pressure. It changes more with low pressure. But I wanted you to see this graph. Think about air pressure change. We're have time on the bottom. So this graph starts out at about 1,012 millibars, maybe 1,011.5 or so, and drops off all the way down to a little below 1,008 millibars. So if I go from 1,012 to 1,008, that's 4 millibars pressure change in 9 hours, from 13 to 22. Same token, I have the pressure at 1,008. It rises up. High pressures come in. We got 1,018 millibars, or 10 millibar rise, and that's over the course of about 15 hours. So horizontally, air pressure really doesn't change a whole lot. If I had you go up a mountain, just a mile up, the air pressure is probably dropped 150 to 100 to 100 millibars, we'll say. Just in a mile. Here, over the course of a whole day, and if you just kept everything the same and could move from one spot to another, you'd probably just have 1,000, maybe no more than 10 millibar Chester change over hundreds of miles. So vertical pressure change is a whole lot more than horizontal pressure change. That influences things later on. We'll talk about that. So here we have the influence of temperature. If I fixed a container and I heat that container, those molecules in that container that are air are going to start to move around faster and faster. They're going to hit the sides of that container more and more. What is that doing? That's increasing the temperature and the pressure in that container. Notice, I said that container was closed. In the atmosphere, you don't have a closed container. So when I heat those molecules, they bump into each other, and what do? They space out further. So if I take a 1 meter by 1 meter box, at one point with one temperature, it has so many molecules in it. I heat it. Now those molecules are hitting each other faster, pushing each other apart. I have less molecules in that 1 meter by 1 meter area. So what happened is the density went down even if the temperature went up. That influences how much the pressure changes. So what you need to know is heated air is going to be less dense and tend to be lighter than cooled air. That's an important thing you're going to want to know. So if the air is very cold, the molecules are close together. If I go up in the vertical, temperature is going to change pretty quickly because all these molecules are packed in there, pushing against each other. So I'm down near the surface, you have the most packed molecules. You get a little higher up, they're not as packed, but they're still quite packed in a cold air. Now, if I go to a warm air mass, it's going to take a lot longer for the pressure to change as I go up in the vertical. Not going to change as much. That's significant as far as how the atmosphere is going to react to form low pressures and high pressures. Also, moist air. It feels like it's hard to move in the moisture sometimes, in the summertime especially. However, less dense air happens when you have moisture. Water has a different molecular weight than normal air. It's actually less. So what happens when you have more water? The air becomes less dense. So if I have a pressure of 1,000 millibars, I add water to it. Well, gee, that air pressure might now be 995 millibars. It changed because of the amount of water went up. So the atmosphere, what I do in the top of the atmosphere impacts the bottom, and what I do in the bottom of the atmosphere impacts the top. It is what we would call a continuous fluid. So I can push air together at the top of the atmosphere. That air is going to want to sink. When it sinks, it moves down, hits the ground, and pushes outward. With what we call convergent air, when air comes together, diverging when it goes apart. I have now increased the air pressure at the ground because the air merged together at the top, pushed it down to the ground, and while it is diverging, it's not diverging as fast as the air coming down. So I'm compressing the air more at the bottom. And this is where you get high pressure systems. Now you've just noticed the flow of the atmosphere. Have a general idea of what the air is doing aloft, at the ground, and on the vertical. So the ideal gas law tells me that pressure, temperature, and density are all related. I already talked about this. So I know 2, I can always calculate the third. All right, air does work. So when air expands, the temperature of the gas drops. Why? Because air had to exert force or effort to expand. So when it did that, it lost some energy. Temperature dropped. You can feel it. It says bike tire. I felt it when I've tried to put air in a tire, my car. However, it's the opposite. When you're pushing air together, you're providing the energy to push the air together. Now it warms up. So if that were the case, and I have air, we know the air pressure is going to decrease as it's going up, right? So as the air is moving upwards, the reason it is cooling is because it's expanding, taking more and more space. There's less of it, so it can take more and more space. It pushes the air apart further. It's cooling. When it's descending, however, if I push an air column down, then what happens is that air is being pushed together. Energy is being absorbed by that parcel of air. We wind up warming. So when air is rising, it tends to cool. When air is sinking, it tends to warm. And here you can see that the air is doing the work. So when I know that, I actually can do an equation and develop how fast the air should cool if it's dry. Notice I said dry. We're not dealing with latent heat here at all. Purely the pressure of the air doing work. So as the air is being pushed up, that parcel of air, it will cool. Basically, 9.8 degrees for every 1,000 meters, or 5.5 degrees for every 1,000 foot. So if you're walking up a mountain or a hill, pressure is going to drop, temperature is going to cool. And now we add in the moist adiabatic lapse rate. All of a sudden, if I have moisture in here and it's cooled to where it's releasing energy into the air, remember, condensation releases heat. So it is releasing a little bit of heat now. So it can't cool, that air parcel can't cool as fast. So air that is wet cools slower than air that is dry. So it's less dense. If it's less dense, things that are less dense tend to float to the top. So if it's less dense from this moist adiabatic elapse rate, that air is going to tend to float above the cooler, drier air. Kind of important for what we're going to talk about. So that's just an overview on air pressure. So let me know if you have any questions.